Okay. So, last class we talked about the linear phase condition and we have discussed all those things. Okay. Now, we talk about how to design an FIR filter or designing of FIR filter. So, commonly FIR filter is designed using three approaches: window Fourier series approach, frequency sampling approach and computer based optimization methods. I will cover only these two approaches because this approach is in computer based optimization. So, what we want to optimize? We want to optimize that filter response so that it matches with frequency characteristics of the given frequency characteristics of the filter. So, my discussion will be focused on these two methods: window Fourier series approach and frequency sampling approach. Okay. So, first let us try about the window Fourier series approach. So, why it is called window Fourier series approach? Do not read the slide first, only listen that audio what I am saying. Just create a thinking in your mind. So, what thinking? Let us say I do not show you the slide. So, what is the thinking? Thinking is that I said windowed Fourier series approach. What is the meaning? So, if I say that the filter response H of n is an infinite series. Suppose I know that H of omega. So, once I know the H of omega, how do I get H of n? By taking the inverse Fourier transform only. So, if I take the H omega inverse Fourier transform, I get H n, which is an infinite series. But I want to design a FIR filter. So, I cannot take infinite series of H n. So, somehow I have to truncate it. So, how do I cut that portion? So, that means I have to design an window which has a coefficient up to length, let us say length L, which is the length of the filter, and after that its coefficients are 0. So, then only I can say I have taken finite impulse in my consideration, not infinite impulse. So, that means if I think that my filter impulse response H of n is derived, although it is infinite, but I cut it to a some length using an window function. So, once I said a truncated length, so I use an window function to truncate infinite impulse response in a finite range. And second condition is that I have to have this one for linear phase design. So, this is my linear phase requirement and this is my FIR requirement, that H of n must be multiplied by an window function which will be defined to cut that impulse response of a certain duration, rest are 0. So, that is my window function. Okay. So, how do I design that filter? So once I say design the filter, then I have to define a window. So, role of the window is cut that H n in a finite duration. Let us the length of the window is L. So, L will quantify, or L is the order of the filter also. Okay. Let us say rectangular window. What is the rectangular window? Rectangular window means up to L the impulse response is 1. So, this is the impulse response of Wn, it is not frequency response, it is impulse response. So, n equal to 0 to L minus 1, all Wn impulse are 1, else it is 0. After L by 1, L by L minus 1, it is 0. So, I define an window which has unit impulse response 1 for a duration L minus L, which is n equal to 0 to L minus 1, elsewhere it is 0. Now, if this is my impulse response small Wn, then what is the frequency response W omega? Nothing but a discrete Fourier transform of Wn. So, Wn is a sequence. I have to apply n point DFT, discrete Fourier transform. Let us say apply n point DFT. So, once I apply n point DFT, so n equal to 0 to n minus 1 signal e to the power minus j omega n. So, which is called discrete, this is called Fourier transform, but signal is discrete, but frequency domain it is not discrete. So, it is not DFT, it is DTFT. When I say DFT, instead of omega, I will write, told me, instead of omega, 2 pi by n. N is the number of discrete point. So, when I say DFT, then this Wk is become same thing, only this omega will be replaced by 2 pi by n into k, nothing else. So, let us do it discrete Fourier transform n equal to 0 to n minus 1 e to the power minus j omega n. So, summation of infinite series becomes like this. Now, if I simplify it, so I know sin theta is equal to e to the power j theta minus divided by 2. So, that principle I applied and I get this one. So, this is the frequency domain representation of this window. If you see, this is nothing but a sinc function. So, there is a window frequency response. So, I have a frequency response of the window. So, when I say I want to design an FIR filter whose specification is given to me, let us say somebody said me that this is my specification, that this is my transition bandwidth, this is the cutoff frequency, low pass filter with a cutoff frequency omega p, and omega s is the stop band edge frequency, and transition frequency is delta, ripples are given, all are given. So, this is my frequency response of the filter which I want. So, when I make it inverse Fourier transform, I get h of n which is infinite in length. I make it finite by multiplying with the window function Wn. Now, if I think in reverse side, that what is the frequency response is this combined portion. It is nothing but a convolution of h omega and window omega. Time domain multiplication, frequency domain convolution. So, exact frequency response what I will get? I will get the convolution between the frequency response by truncated filter along with the window function frequency response. So, window function play an important role to define how close I approximate this one, because I have to approximate this one. But this, since I use a window function for a FIR filter, this approximation will be disturbed. So, how much approximation, close approximation I can make, that depends on the window function. So, what is there? So, if I say window function has a main lobe and has a side lobe, what I discussed during that your discrete Fourier transform. So, any window function has a main lobe and has a side lobe. Okay. So, main lobe, if I want to design and filter, so main lobe must be here and side lobe is the produce the ripple in stop band, and main lobe is give me the pass band frequency. So, window has a role to design or to characterize the filter frequency response. So, that is why people have designed different window for different purpose. Rectangular window. The main lobe width is small, but it has a very much ripple in side lobe. So there is a lot of window is there. Blackman window, Hamming window, Henning window, Kaiser window. So those window function I have already discussed during my discrete Fourier transform discussion. So there is a lot of, or STFT, when I talk about the STFT, we have discussed a lot of this. And every window function has its own frequency response. So those R is nothing but a W omega. So we collect some sample of, let's say 300 sample of window using this function. How do you do the frequency response? Let's this Blackman window. So I varies n from 0 to 300. Let's 300 sample I am collecting using this window, and then what I do, let's say I do a DFT of 300 point DFT. Then if I plot it, a magnitude plot, only the magnitude plot of the Fourier transform, I get this kind of plot. So Hamming window, rectangular window, Hamming window, Henning window, Butterworth window, Blackman window. So if you see the Blackman window, main lobe is wide and side lobe is also very much attenuated. But here main lobe is very narrow and there is a lot of ripple in the side lobe. Here also main lobe, lot of ripple in the side lobe, but attenuation in the side lobe is much higher. Here if you see, the main lobe is wide, but side lobe is also some attenuation is there. So depending on these characteristics, this is the relationship between the window function and peak side lobe and transition bandwidth in the main lobe. So what is the relationship? So if I say, let's say I want to design a filter, let's say I take an example. So I want to design and filter using Hamming window. So what is the, if you see, when I say the Hamming window, I know peak side lobe is minus 43 dB. So if I require a very much attenuation in the side lobe, then I can go for Blackman window minus 58 dB. So if the stop band attenuation is my important factor, then I can know the which window I will use. If I say no, stop band attenuation is not that much of important factor, then I can say I can use rectangular window because it has a less transition bandwidth. So if you see, this is the relationship with the transition bandwidth. What is the transition bandwidth? When you design the filter, the distance between the stop band frequency and edge stop band frequency and pass band frequency. So omega s minus omega p is my transition bandwidth. So when I in decreasing the side lobe peak side lobe attenuation, then I can see my transition bandwidth is increasing because it is nothing but a 8 pi by m. M is the order of the filter. So what is happening? If I choose very much good attenuation in side lobe, then my transition bandwidth will be increases. Let's say suppose somebody said that design an FIR filter, write down in your pen and paper and then try to do that. Pause the video here and write down the problem in a paper and then try to solve it by you first and then see the video and see what you have done wrong. Okay? Let's say I given you a specification, design an FIR filter. I have to design an FIR filter whose FIR low pass filter. Let's say FIR low pass filter. Design an FIR low pass filter whose cutoff frequency, let's say cutoff frequency Fp is equal to 2 kilohertz. Transition bandwidth is equal to 300 hertz. Okay? Let's say I said peak side lobe attenuation is minus, I required minus let's say for 50, let's say 46 dB, or let's say minus 40 dB, let's say minus 40 dB. I require minus 40 dB. As I said that I have shown you a real specification of a filter: peak side lobe attenuation, peak side lobe attenuation, peak passband attenuation. I have showed you. So that is required minus 40 dB. Now, if this is my requirement, then what window I should choose first? Because I said I require minus 40 dB attenuation in peak side lobe. So if I see here only this is 30 dB, so I cannot use Hamming window. I have to use Hamming window. So I use Hamming window. So Hamming window, I know the transition bandwidth is nothing but a 8 pi by m, where m is the order of the filter. So what should be the order of the filter? How do I determine? So m is equal to 8 pi by delta. Now if you see, this is in radian, and this, if I cannot define, this is in hertz, so I have to make it radian. So if my delta is equal to 300 hertz, so if I say it is normalized discrete frequency, and let us say sampling frequency Fs is equal to 8 kilohertz, then how I have to convert 300 hertz into radian first. So how do I convert? I know 8 kilohertz means 2 pi. So 2 pi divided by 8 kilohertz into 300 hertz. So I can say 6 pi by 80. So if I divide it, 8 pi divided by 6 pi by 80. So pi cancel, it is nothing but 8 into 80 divided by 6. So it is nothing but let us say 320 divided by 3. So I can say it is nothing but a 1, then 0, then I can say 6 point something. So I can say let's 107. So the order of the filter m is equal to 107. Now if I know h of n, then I can convert with my input signal x of n, I get the filtered output signal. So my next step is to how to find out h of n. So first, specification to discrete frequency conversion, relations between the transition bandwidth and order of the filter. So if my transition bandwidth is 300 hertz, my order of the filter using Hamming window is nothing but 106. Now in the reverse way, somebody said order of the filter is 200. What should be the transition bandwidth? You can easily calculate. So either transition bandwidth or order of the filter, both way you can calculate. So from this relationship, what I get either m or I can calculate the transition bandwidth, and this relationship give me the which window I should choose. So I know that which window I have to use. I know what is the order of the filter. Okay. Then I use the Fp and Fs to compute the Hn. So next step, I have to compute the filter coefficient. Okay. So when I want to design window Fourier transform, I have to compute the filter coefficient. So how do I compute the filter coefficient? How do I do that? So developed an expression for the discrete frequency response of Hk. So from the given specification, you have to develop the Hk. This is my Hk. So k is discrete frequency. Then apply inverse DFT or IDFT to get Hn. So once I know this one is my Hk. So I can use IDFT to get h of n. So this is the procedure. I can, as a function of Hn is a function of expressed as a function of time. So let's, H omega is the frequency response of a low pass filter response is Hn. So I have a low pass filter. I know that low pass filter frequency response is H omega. So H omega is nothing but this one. So what is Hn? Is nothing but an inverse Fourier transform. So if it is discrete time Fourier transform DTFT, then inverse one is minus pi to pi h of omega e to the power j omega. This will be plus d omega. But this one is infinite in duration. So I have to truncate it n minus 1 point for a filter whose length is n, not m, n, which is equivalent to Hn by n window function. So let's say this is my low pass filter frequency response. What is required? Up to omega c, this is 1, amplitude is 1, else it is 0. This is my requirement. Omega c is the cutoff frequency. Okay. Now a delay m minus 1 by 2. So m is the order, m is the order of the filter, m minus 1 by 2. So m minus 1 by 2 unit is incorporated into H omega. So why this term is incorporated? Because what is required? I require this will be all 1 and rest were. So up to 0 to omega c. So what will be H omega? Basically I have to write H omega up to 1 0, 0 to omega c, this will be 1 for every omega and elsewhere it will be 0. I incorporate another term which is j omega m minus 1 by 2. M is the order of the filter to make it linear phase. So forcing the filter to be length m, and I incorporate this one because I want the filter should be linear phase. So I incorporate this part. Then for a rectangular window where m is odd, let us say m is odd, rectangular window and m is odd. Rectangular window, m is odd. If you do that, then you can calculate h of n. So h of m minus m is the order of the filter. So m minus 1 by 2, it will be omega c by pi and rest were. So you know that h omega is nothing but a h r omega into e to the power that part. So h r omega is this one for m odd. Rectangular window means 1 up to that part and 0 afterward. So I can get this one. So this is my Hn. So Hn, expression of Hn is equal to, so I get h of n is equal to sin omega c into n minus m minus 1 divided by 2 divided by n divided by pi into n minus m minus 1 by 2. Okay, and h of m minus 1 by 2 is equal to omega c by pi. So this is n equal to 0 to m minus 1 except m minus 1 by 2. So except n is not equal to m minus 1 by 2. This is this one. And when n equal to m minus 1 by 2, this is nothing but a omega c by pi. Now suppose I told you, write a program to compute the H0, H1, H2 for, let us the length of the filter is 300 300 is the length of the filter. So compute 300 coefficient of Hn. Compute 300 coefficient of Hn when this equation is filter coefficient is expressed by this one. What is omega c? Omega c is the cutoff frequency. Let's the cutoff frequency is 2 kilohertz. Then what is the omega c value? Let's this filter is designed where the sampling frequency is 8 kilohertz. So I know omega c is nothing but a 2 pi fp divided by fs. So it is nothing but a 2 kilohertz divided by 8 kilohertz. So it is nothing but a pi by 2. So omega c is pi by 2. So I know the value of omega c. I know the value of omega c. I can now I produce H0. So H0 n equal to 0. Sine of omega c is nothing but a pi by 2. N equal to 0 minus m minus 1 by 2 divided by pi into n minus n equal to 0 minus m minus 1 by 2. I get the H0 value. Then I get the H1 value. Then I get the H2 value. Now if it is odd, so order is 301, let us say 301 is the odd. So if it is m minus 1, so 301 minus 1 divided by 2, which is nothing but a 300 divided by 2. That means n equal to at n equal to 150, this will be only omega c by pi. So pi by 2 divided by pi. So pi by 2 divided by pi means half. So that way I can calculate H0, H1, H2 and I can get the filter coefficient, and once I get the filter coefficient, once I find out the filter coefficient, I just make it convolve with that my input signal to get the output. Is it clear? Is it clear? Okay. So this is the procedure for design FIR filter. First you define your H omega, then you develop that what is your expression of Hn. Once you get it, then you can design the filter. Once you design, because you know that m is odd or n is even, what is the equation of that? I get that filter frequency response. Okay. So this is the filter FIR filter design using window Fourier methods. So you can calculate, you can try with many filter design either using MATLAB or you can write a C code for this filter design. Can I told you write an low pass filter C codes in C programming language or in MATLAB programming language. Don't use that filter function which is already installed in the MATLAB. Then you should not get the inside of that filter. So if you use the toolbox only, then you define the frequency and then toolbox will design the filter for you. But at least you know what are the input parameter you are giving and what the implication of those input parameter in the output, you know, once you know that how to design an FIR filter. Okay, thank you.